Yes.
So I'm quite happy that I can introduce here Luca Corsaro and Mohsen Dehghanpour for presenting their topic related to thermographic analysis of cyclically loaded specimens and fatigue limit estimation using AI or machine learning. In this case, I believe rather that way. And I'm quite interested in that because this is something which I learned for the first time from Torino, from Raffaele Cesana, and we introduced it a bit as regards the thermographic analysis into Czech Technical University. And so I'm very interested what our colleagues in Torino, our predecessors, I would say, master to do with AI involvement. Luca and Mohsen, the place is yours.
Okay, thank you, Jan. I'm sharing the screen. Can you see our screen?
Yeah, we see it. If you can switch to presentation mode.
Yes. Is ready now?
Yep. And
okay.
And information to other colleagues. If you find something which you would like to discuss, there are two options. You can wait till the very end. By the way, Luca and Mohsen, do you have page numbered? Pages numbered or?
It is around, no, pages number, no, unfortunately, no.
So in that way, because we do not have reference number, please do not hesitate to either raise a hand or even to interrupt Luca or Mohsen with a question. Yeah,
yes,
so we can respond really to something what is in that moment important. Thanks a lot. Go on, please.
Yes, for any doubt, please feel free to interrupt us for discussing. So thank you, Jan, for the introduction. Today, my colleague Mohsen and I are presenting an overview of our research activity conducted here in Politecnico di Torino, entitled Thermographic and Machine Learning Approaches for a Rapid Fatigue Limit Analysis. This research activity aims to find possible connections between the fatigue limit and the thermographic method by means of artificial intelligence aspects. As is well known to all of you, the fatigue limit is a crucial mechanical property to ensure the correct functioning of mechanical components under working conditions. And regarding the assessment of this mechanical property, the thermographic method is a fast methodology for the fatigue limit analysis, and the evaluation is carried out by using the thermal emissions produced during the fatigue test. Regarding the artificial intelligence aspects, machine learning techniques are very powerful algorithms to predict a trend with a high level of accuracy. So the results obtained from this preliminary research activity lead to an optimization of the thermographic method by using machine learning techniques, as we will discuss during this presentation. This works consists of several parts. The thermographic method and the machine learning techniques are introduced. Then the experimental activity carried out in this work is presented, and the last part is related to a discussion of the results and the conclusions of this research activity. The thermographic method is an alternative approach to the classical staircase analysis for the fatigue limit assessment. And oh, sorry, I didn't see our... okay, sorry. Okay, can you see our screen?
Yeah, we can.
Okay, sorry. No, once again. Okay, sorry. As I said before, the thermographic method is an alternative approach to the classical staircase methodology for the fatigue limit assessment. And this methodology adopts the thermal emissions produced during the fatigue test. This slide reports an example of a thermal profile obtained from the thermal emissions. This thermal profile is extracted from a region of interest located over the surface of the sample from the thermogram. This thermal profile is characterized from a transient trend followed by a stabilized trend. This stabilized trend may remain stable in case of a stress amplitude lower than the corresponding fatigue limit of the material. On the other hand, this stabilized trend may increase its evolution with a rapid temperature increment in case of a stress amplitude higher than the corresponding fatigue limit of the material. The thermomechanical equilibrium behind the thermal profile is reported in this slide. Boulanger and his colleagues present this study, and the thermomechanical equilibrium consists basically of two parts. On the left side, there are differential operators applied to the temperature in terms of time derivative, spatial analysis. On the right side, there are different heat sources involved during the heat generations. And the first heat source is related to the intrinsic dissipations, and in this case, the heat generation is produced within the material when the specimen is subjected to a certain load. The second contribution is the thermoelastic source. Then the third heat source is related to possible internal coupling source with caused by the microstructural state of material when it is subjected to a certain load. And the last contribution is referred to possible external heating sources. Then the thermomechanical equilibrium can be simplified to consider the infrared image processing, and the hypotheses are listed on the left side. In particular, there are constant density and specific heat, negligible convective terms. The conductive tensor is constant during the fatigue test, and the external heating sources are considered independent of time and with the aim of satisfying the equilibrium temperature field reported here. And the last hypothesis considers that the temperature variation due to the fatigue test does not influence the material microstructure. So at the end, the thermomechanical equilibrium can be simplified considering just the temperature variations and its sources due to intrinsic dissipations and thermoelastic effects. Focusing to the intrinsic dissipations, the factors involved during the heat generations are different depending on the load. In case of low stress amplitude, as an example below the fatigue limit, the heat generation is mainly caused by the inelastic phenomena. On the other hand, in case of high stress amplitude, as an example above the fatigue limit, the heat generation is mainly caused by movements of dislocations or microplasticizations effects. In order to investigate the intrinsic dissipations produced during the fatigue test, thermal parameters have been properly developed over the years, and the thermal parameters are calculated from the thermal profiles obtained from a certain fatigue test in which a certain stress amplitude is adopted. The first possibility is the thermal area, and basically consists to the area subtended to the thermal profile. The second possibility is the thermal increment, which consists to a temperature increment of the thermal profile. And the last possibility is the thermal gradient, which takes into account the transient zone. These thermal parameters are calculated from for a certain number of fatigue cycles, and in general, this value is less than 200,000 fatigue cycles. Then the fatigue limit is estimated analyzing the thermal parameters evolution as a function of the stress amplitude adopted during the fatigue test. The fatigue tests are interrupted when an abrupt thermal parameters increment is detected during the thermal parameters evolution. And each of these circles corresponds to a certain thermal parameter calculated from the thermal profile obtained during a certain fatigue test with a certain stress amplitude. And from this graph, there are mainly two different trends. There is a flat trend near the low stress amplitude as a consequence of the inelastic phenomena involved during the fatigue test. On the other hand, there is another trend which corresponds to an abrupt thermal parameters increment, and this trend occurs for high stress amplitude, and this trend is mainly caused by the dislocations movement or the microplasticizations effects. So at the end, the fatigue limit is located between these two trends. So the fatigue limit at the end is estimated by using the two curves method. This methodology is an automatic routine able to split the thermal parameters evolution on the basis of the nature of the intrinsic dissipations, and then the fatigue limit is calculated from the intersection of approximating curves adopted to mathematically describe the thermal parameters evolution. There are several possibilities in terms of approximating curves. As an example, linear approximating curves, which means that the thermal parameters evolution below the fatigue limit are approximated by using a linear mathematical formulation, as well as for the thermal parameters evolution above the fatigue limit. Another possibility is the parabola power law approximating curves, which means that the thermal parameters evolution below the fatigue limit is approximated by using a parabola mathematical formulation, while the thermal parameters evolution above the fatigue limit is approximated by using a power law mathematical formulation. Then there is another possibility that consists to set a constraint to the zero value for the mathematical formulation related to the thermal parameter approximation below the fatigue limit. But at the end,
Luca, may I interrupt you with one question non-related to AI?
Yes.
You told us that this thermal increment is, in your case, evaluated in 200,000 cycles. Did I understand it right?
Yes. In general, the thermal parameters, the thermal profiles is recorded for a very short number of fatigue cycles. But Mohsen and I will discuss about this in the next slides.
Very short time is how many cycles, please? If I get it right.
Sorry?
How many cycles you set? You should short profile.
In our experimental activity, we used 150,000 fatigue cycles for detecting the thermal parameters evolution.
That's quite long history.
Sorry?
150,000 cycles?
Yes. During each fatigue test conditions.
I see. Okay, well, that means that it's quite a demanding, say, load profile, which causes that basically you cannot use a step test because of the durability of the specimen is very quickly exhausted.
But in general, we performed not. The idea is to start with very low value of amplitude of stress amplitude, and
that's
then
that's the lower curve, yeah. But
yes,
the second part, Either you will get very quickly to exhaustion of the fatigue resistance of the material. So you
Yes.
make, for example, just 2 or 3 steps, and then
Yes,
you have to
exactly.
interpolate on a very small number of specimens, or you need more specimens for that.
No, but in general, one specimen is enough.
Yep.
Yes.
Okay.
Because in general, the number of points in this part where there is an abrupt thermal parameter increment is not more than 2 or 3 points.
So this is enough for you. Okay, that's the important point. Thanks a lot.
Yeah, yeah. Can I continue?
Yeah.
Okay, so um, at the end, the most appropriate choice in terms of approximating curves or in terms of thermal parameter depends on the experience or on the material or on the load applied during the fatigue test, or in general, the evaluation is done on the basis of the thermal parameters evolution obtained during the fatigue test. So the thermographic method has advantages in terms of rapidity and non-destructive approach. The reason is mainly due to the fact that the number of cycles is less than the classical run-out condition involved during the staircase methodology. And finally, nevertheless, the fatigue limit can be estimated by using just one sample. On the other hand, the possible results variability on the basis of the approximating curves or the most appropriate choice of the thermal parameters lead to possible disadvantages for the thermographic method. But from this research activity, we have seen that these disadvantages can be reduced by using machine learning techniques.
Yeah. So thanks to Dr. Corsaro for the introduction. Now I will introduce a little bit about the machine learning technologies and or the machine learning use of technology as a facilitator to reduce the disadvantages that already Dr. Corsaro mentioned. So I'm not an expert in mathematics. I'm a mechanical engineer, and here I'm not going to be in depth technical with the core mathematics of machine learning, but I think that is these type of technologies and these type of tools could be used as facilitators to increase and to enhance the output results in the realm of mechanical engineering. So as Dr. Corsaro said, one of the most disadvantages of the TCM two curves method, fatigue life estimation as an NDT technique, is the high uncertainty. So you can have a batch of high results, high variable results from each other with a wrong range threshold. And as Dr. Corsaro said in this slide, choice of the thermal parameters is completely based on the experimental campaigns that you are delivering. So we were thinking that maybe machine learning could be useful. So just to have a general mind that is not covering all the machine learning techniques, but we can categorize the machine learning technologies into 5 main categories that is written here: supervised, unsupervised, semi-supervised, reinforcement learning, and deep learning. And in supervised learning, we could subcategorize the techniques into the regression models and classification models, which in the regression models, the support vector regression or support vector machines, Gaussian process regression, and artificial neural networks is widely used. And I think some of the audiences already know that the neural networks is the core technology of the LLMs, large language models that we are using, or some of us are using widely nowadays, like GPT and so on. So if I want to go further into regression models, support vector machines or regression techniques, SVR or SVM, has designed to expand the SVM framework for continuous output evaluations. SVR is a nonlinear issue handling extension of linear regression. SVR's kernel technique makes it flexible and reliable way to interpolate, and it produces a very fast and a bit reliable. If I want to say it in easy words, easy to get, I call the SVR the deterministic workhorse. So it will extrapolate the whole data set into a 3D realm. It will plot a surface that is the best fit into the 3D scheme that is already been scattered of the data set. It will reproject the plot into the 2D realm, and it will announce that best fit plot to you. So by hyperparameters like cost, epsilon, and gamma, you can fine-tune the model to avoid overfitting, to predict exactly your data set and your data points. That is not the case in our research, because we want the interpolation between the real points, real pages of stress amplitude and thermal parameters, but generally we have to be aware of overfitting. So the setup of SVRs is defining modified regression function, like kernel function or a regularization function. Use selected standard solver to solve likelihood function, and finally you will have the interpolated outputs, and you can find posterior distribution coefficients. That in our case, since we wanted to have the best fit interpolated data into our real experimental campaign data set, SVRs is not a good choice. So the next one is Gaussian process regression, or GPR. Unlike the SVR, GPR, if I want to tell you in, again, simple words, I will call GPR the probabilistic conscience. It will give you a batch of probability of best fit curvatures or points with a limited and defined threshold of deviation, which can guide you where you have to redo your experimental campaign. So it's a very powerful tool and technique of machine learning to guide you where do you have low accuracy metrics, and where you have to redo your experimental campaign. It provides, as I said previously, probabilistic interpretation and helps guide the research for the best solution. GPR's kernel technique makes it flexible and reliable way to interpolate. Two most important parameters of the GPR setting up is S-squared, exponential, and rational quadratic are the two common GPR kernel functions. So to set up GPR, in simple words, you have to define the modified regression function, like kernel function and noise function. Use, again, selected the standard solver to solve objective function, and having your interpolated outputs and coefficient and intercept factors. So again, if I want to be more accurate, I can say the technology that I love to use is artificial neural networks. If I want to generally simplify artificial neural networks into simple words, I can say that neural networks is the nearest technology to human brain. So from 1950s and 1960s, neural networks has been evaluated by inspiration of human brain. So they are the structure, the core structure of neural networks contains of limited numbers of layers. In each layer, you can define numbers of neurons, in which in each neuron you will have a function that these layers, neurons and function together, will learn from the input data set that you can define for them, even qualitative, even quantitative, and you can have your output preferred result, like interpolation, extrapolation, whatever you are wishing from the neural network. Obviously, it is not unlimited or illimited, it is limited, but it could produce the best. So in our work, we used a feed-forward neural network, fully concentrated. The input layer was set the stress amplitude and the thermal parameters. We used 3 hidden layers. In each layer, the first layer 128, the second 64, and the third 32 neurons. Obviously, we use ReLU activation batch normalized to stabilize training, and we use a 20% dropout to avoid overfitting, and L2 regularization, and we use Adam optimizer coverage less than 200 epochs, which is a normal setup for artificial neural network. And maybe some of the audiences, dear audiences here, will ask me that, Mohsen, why, from the first place, you used machine learning instead of genetic algorithm, or instead of conventional fit curving methodologies to interpolate, to enhance your data set? Because of two techniques, because of two very important issues. The first is that by use of neural network, if you see here in the slide that dear Dr. Corsaro said, then you are going to enhance the number of data sets by interpolating. In the conventional technologies like genetic algorithm or conventional curve fitting methodologies, you will demolish this zone that is between the analytic phenomena and dislocation zone. So you will need a technology that even it produces the points, even it will enhance the data set, it realizes the difference between these two zones, so the TCM would work. In other case, the TCM wouldn't work. So this is one another thing. And the another issue was that obviously the machine learning techniques are so strong and are so accurate. So in that case, we could reduce the uncertainty so much. So for evaluating the machine learning technology, we will have the accuracy metrics that obviously the audiences know them, like mean squared error, RMSE, mean absolute error, MAPE, and R square. Generally, we use RMSE and R square to evaluate and check the validity of our models.
Okay, let's move on to a brief discussion of the experimental activity. The specimens adopted during the fatigue test are reported in this slide. The specimens were made of C45 steel, and the geometry is reported in these two pictures. So a cylindrical geometry was adopted for the specimens. And the experimental setup is reported in this slide. This picture reports the mechanical pulsator adopted for the fatigue test. And regarding the thermal emissions acquisition, in order to estimate the fatigue limit by using the thermographic method, the thermal camera was placed in front of the surface of the sample during the fatigue test. And the table on the right side reports the stress amplitudes adopted during the thermographic approach and the corresponding number of fatigue cycles adopted during the thermal emissions acquisition. This slide tries to summarize, to explain and to summarize how the thermographic method was combined with the machine learning approach. So the thermographic method approach was adopted in order to detect and to investigate the thermal parameters evolution as a function of the stress amplitude. Then the transition zone was properly optimized by using the artificial neural network technique. And then this optimized dataset was adopted inside the two curves method routine for the fatigue limit estimation. The results in terms of fatigue limit by using the staircase methodology is reported in this slide. The table on the left side reports the testing conditions adopted during the experimental campaign, and on the right side, the graph regarding the trend between the survived and failed specimen is reported. Then the fatigue limit estimated by using the staircase methodology was around 210 megapascal. So this was our reference value in order to compare the results obtained from the classical thermographic approach and the thermographic approach improved by using the artificial neural network technique. The thermal emissions prior to the fatigue limit analysis by using the thermographic method is reported in this slide. The thermographic activity was carried out with two experimental campaigns in order to provide multiple results for this research activity. The graph on the left side reports the thermal profiles obtained during the fatigue test. the solid line refers to the first experimental campaign, while the dashed line refers to the second experimental campaign. And the blue colors report the thermal profiles obtained with low stress amplitude, while the red color refers to the high stress amplitude values adopted during the fatigue test. The thermal parameters evolution as a function of the stress amplitude are reported on the right side. The thermal parameters adopted in this research activity was the thermal increment and the thermal area. And the circle symbol refers to the first experimental campaign, while the X symbol refers to the second experimental campaign. And as you can see, there are differences in the thermal parameters in the transition zone. This slide reports...
May I ask you, please, Jan, again?
Yes.
Thermal area, this is area to this reference number of cycles of 150,000 cycles?
Yes.
So up to this point, everything what is below the thermal curve is the product, gives the product of thermal area.
Yes, each of these points is the thermal area. So the area subtended to each thermal profile. So as an example, the blue line refers to the test one in which 100 megapascal was adopted. So this point refers to the area subtended to this first blue profile.
Thank you.
The second thermal parameter and so on. Okay. Okay, this slide reports the results in terms of fatigue limit estimation by using the thermographic methodology, but without any improvement of artificial neural networks. The analysis was carried out by using these two thermal parameters, the thermal increment and the thermal area, but also by using different approximating curves, the parabola power law approximating curves and the linear possibilities, but also investigating the possibility to set a constraint for the mathematical formulation below the fatigue limit. And as you can see, there are differences, as an example, between the approximating curves adopted to mathematically describe the thermal parameters evolution, because in one case there are results around 200 megapascal and in another case 140 megapascal. But there are variability in the results also in case of different thermal parameters, but by using the same approximating curves, because here we obtained more or less 200 megapascal and 130 megapascal. So the method is a very fast methodology for obtaining a fatigue limit if compared to the classical staircase analysis. But the most appropriate choice in terms of approximating curves or thermal parameter is could be a disadvantage for this methodology. This slide is...
Luca, can I interrupt again?
Yes, I'm here.
And no zero passage means what? This is about the first part of the thermal curve?
Yes. We have
zero, zero.
Yes, we have classified on these two main columns that are split on other two columns on the basis of the experimental campaign, the possibility to fix a constraint to the zero for the mathematical formulation referred to the values below the fatigue limit, because in general in literature there is this possibility. So
it's quite logical to get zero at zero. Yeah, so thanks.
Okay. This slide is just to explain very fast how the thermographic method, the two curves method routine works. On the left side, there are the results obtained from the first experimental campaign, and on the right side, the results for the second experimental campaign, referring the approximating curves to the parabola power law approximating curves. So as you can see, this vertical line is the intersection of the two different approximating curves, And the dashed lines are referred to the parabola mathematical formulation adopted for the thermal parameters approximation below the fatigue limit, while the solid line refers to the power curve mathematical formulation adopted for the thermal parameters evolution approximation above the fatigue limit.
Exactly. So if I want to just focus a little bit, few more seconds on this slide, you can see this range is the range of uncertainty, as is written here, uncertainty range. So you can see the TCM method is fast, but in terms of reliability, due to the high range of uncertainty, it could not be considered as the most reliable technique in comparison with the staircase methodology. So you see that from upper 150 to a little bit upper than 200 is the uncertainty range. In comparison with the staircase method, that the exact number is 211 megapascal with the standard deviation of 5 megapascal, positive minus 5 megapascal. So here is the magic of ML, which happens when we interpolate the data into the central zone by considering and not avoiding the gradient demolishing between the analytic zone and the microclassization zone, we will see a very, very significant reduction in uncertainty range. So if you see this slide, we could see the lowest number as 117 and the highest number as 208. But here, with the help of machine learning, we will see that the lowest number will become 179 and the highest number will become 213. Another advantage of using ML that Dr. Corsaro said in the previous slide, it is completely, the TCM, it is completely relied at the configuration that which configuration by considering the zero passage or not considering the zero passage, but by considering the thermal parameter like thermal area or thermal increment or approximating curves, it is completely dependent on this type of configuration. But with the help of ML, we removed another type of dependency. We again reduced uncertainty. You can see that the staircase reference was 211 with the standard deviation of positive minus 5 megapascal, and this whole configuration with not considering the zero passage, irrelevant and independent of the linear or parabola power law approximating curve or independent to the thermal increment or thermal area, all of these results could be considered as a valid result, as a reliable result. So again, ML did do, I can say, a very huge job to reduce the uncertainty of the classical TCM method. And for the final slide of the results, if we consider and if we compare the absolute error in percentage between the classical TCM and enhanced TCM with ML in comparison with the staircase reference value that is 211 megapascal, you can see that we decreased the absolute error from 42.18%, for example, to 1.4%, or from 34.6% to 10.4%. And again, in this configuration, we will see all the absolute errors in the TCM that is enhanced with ML is below 1%. That is absolutely valid and reliable. So for conclusion, I can say the implementation of ML technique resulted in enhancement of the original datasets, which respect to those obtained from the original experimental campaign. The second one is improved dataset led to decreased uncertainty in significant values by means of lower variance and better accuracy metrics. Actually, if I want to say one of accuracy metrics that were derived in this research, we developed the R square from 91% to 97%, or we decreased the RMSE on thermal parameter from near 60%, from 0.019 to 0.008. So these are the main conclusion at the side of ML that enhance the dataset.
And from the fatigue limit estimation point of view, a reduction in the variability was observed among the approximating curves and the thermal parameters adopted for the analysis, and the whole developed technique led to a reduction of the amount of time in the experimental campaign for the assessment of the fatigue limit. So thank you for the attention.
Thank you. Thank you so much.
Thanks, Luca and Mohsen, and please, the space is open for a discussion. Any comments from colleagues here? Questions? Don't be afraid. Well, before somebody asks, yeah, I have to say I'm currently on a holiday, so my wife interrupted me in a very important moment, and I didn't get the point. How big is the set used for training? Because if you presented results of your analysis, where I expect that the machine learning model was trained on some previous data set. Am I right?
We have changed not changed, we have optimized, if I have understood correctly the question, we have just considered the central zone in the thermal parameters evolution, and we have improved only this part for improving the fatigue limit estimations, but not in terms of results, because results in general are very good results by using the classical thermographic method. But the problem is the uncertainty produced by the method in terms of choosing the most appropriate combination of approximating curves, thermal parameter, because in general are based on the experience. So the most appropriate choice in terms of thermal parameter was the thermal increment, because we obtained a very high thermal increment during the fatigue test, and the most appropriate approximating curves are the parabola power law approximating curves, because thermal parameters evolution was more or less as a power trend. So this choice is made on the basis of the experience, but we want to try to remove this experience, this dependence on the basis of the experience. And we want to try to uniform as much as possible the results.
Right. But I have to say that this type of solution is new for me, so I apparently didn't understand the solution well enough. Okay, thanks for the explanation.
But if you want, we can discuss about it. Maybe I have not understood.
No, I think that's good enough. Yeah, I understand now that this goes other way than I am used to. Yeah, that's all. Other colleagues here, please.
If I can ask something, I've seen in the test that you stop the fatigue test at 150,000 cycles.
Yes.
And from these tests, do you extrapolate to find the fatigue limit?
Yes, the idea is this. You start with a certain amount of stress amplitude, and you test this stress amplitude for a certain amount of fatigue cycle, as in general less than 200,000 cycles. Then you increase the stress amplitude, and you repeat again the test with the same number of cycles, and so on, until you are able to detect a thermal parameters, an increment in the thermal parameters evolution. This means that the intrinsic dissipations produced during the fatigue test are referred to a very special effects, in particular the movements of dislocation or microplasticization, that in general occurs for stress amplitude higher than the fatigue limit. This means that the stress amplitude tested during the fatigue test are higher than the fatigue limit. Then you run the two curves method routine, which is able to find these two different trends that are basically produced from two different nature of the intrinsic dissipation. Below the fatigue limit, an elastic phenomena. Above the fatigue limit, so a very an abrupt trend, so a very rapid trend. This trend is produced by microplasticization effects. Then the intersection of this mathematical approximation lead to the possible fatigue limit of the material.
explanation for Angel. This is not a common fatigue test. It really
Yes,
is based
exactly.
this is based on thermal observations, what's going on in material, if this is over elastic limit or if there are some microplastic
Yes.
issues and so on. Because of this generates a different heat.
Yes,
Recognition if the heat is high enough or not enough gives you this thermal curve.
Exactly.
Yes, exactly.
And dear Jan, just to mention that since we are testing lower than the amount to be destructive for the material, so we do not know exactly when the change occurs from the analytic zone to the microplasticization zone.
Microplasticization.
Exactly. So that's the case when the uncertainty happens. That's the case that you have a long range of possible results from 170 megapascal to near 208. So, and it will be dependent to the configuration of the curvature or thermal parameters or so on. So that's when the machine learning could enhance the data set, could interpolate and strengthen the data set. So in this case, the number of possible results would be reduced significantly, and you will have a very near result to the staircase reference number.
If
Yes,
I could interpret it in a way that it removes the, say, personal bias and the attitude of the observer, because of it's trying to find out the best Gaussian distribution for
and simultaneously preserve the trend from not being demolished. So you will not have a trend that you cannot see anymore the change of the trend. So you have to preserve the trends, two trends separately. Moreover, you have to strengthen the data set. That is the whole idea.
Yes, for this reason, we started from the classical thermographic approach because we want to investigate the overall thermal parameters behavior. Then we can stop the fatigue test. Then we go in detail in the transition zone that it is highlights very well. And then we have optimized this transition zone with other points. And this way we can run again, we can run this new optimized data set inside our two curves method routine, because otherwise we have not enough points for finding with a very well accuracy the fatigue limit if we just consider the transient zone.
Okay. May I have one question? How many specimens you destroyed for this heat observation?
I performed the experimental test by using not more than 3 or 4 samples, because I want to be sure to detect the thermal parameters evolution above the fatigue limit. But in some cases, you can use just 1 sample.
And have you observed some scatter between different specimens?
Yes, if you, maybe I can share again my screen. There was differences between the two experimental campaigns in the transition zone.
And by the way, what was the final surface quality for these specimens?
It was a classical ground surface.
So just a ground surface, no polishing.
Here. The thermal parameters are not overlapped in the transition zone where the fatigue limit occurs, but you can also see this behavior in the thermal profiles evolution.
Yeah, but I would say this is a minor scatter compared to some results of us.
For sure.
This is awesome.
Yeah, for sure. We are in the transition zone where the fatigue limit is.
Okay. So other questions, please. I would maybe mention that if everything proceeds well in the July, this is 24th or something like that, there should be another lecture by Alek Karolchuk on using Gaussian processes for multi-pixel fatigue estimation. So We can stay with Gaussian processes for quite a long time. Other comments and questions, please, colleagues? Okay. So if this is all for today, thanks for taking part. Thanks to Luca and Mohsen for presenting this interesting presentation. And I hope we will find some time for cooperation on the topic later on.
Sure. Actually, just to add one other point there, Jan, we was going to present our work because, you know, nowadays AI is entering all the realms of different types of engineering.
Yep.
So now we are in the era of AI. So we just wanted to present, and obviously we are not the experts of AI. Obviously, we are just two engineers try to find a way, try to facilitate the fastest destination.
Any bit of experience is quite useful for everybody.
Exactly. So if there is any opportunity for any other members of the group to be involved in the collaboration, to be involved in some cooperation between Politecnico di Torino, Texel Group,
Yes.
and other colleagues, that would be fantastic. So I will invite with all of our honor and will of all of our hearts, and that could be a great opportunity to collaborate with each other.
Okay, thanks.
Thank you.
So that's all for today. You have the last chance to say something. I mean those silent here. Nobody wants to say anything. I'm stopping the recording.